Welcome to this lesson on congruent triangles as well as isosceles, equilateral, and right triangles. We'll have a few slides that I will talk about in some detail here at the beginning. This first concept, CPCTC, is going to be crucial for you to understand. It's an abbreviation for corresponding parts of congruent triangles are congruent. What this is based on is that anytime you have proven that two triangles are congruent, you can then say that any of their corresponding parts must also be congruent. But you cannot use CPCTC to prove triangles are congruent. That is the biggest mistake made in these types of proofs in geometries. People think they can say, well, these two triangles are congruent by CPCTC. Absolutely not. You have to use the side, side angle side, and angle side rules to prove the triangles are congruent. Once you have done that, you can then use CPCTC to prove that individual pieces, for example, angle A is congruent to angle D between two triangles. You can prove the individual pieces are congruent with CPCTC. Here we have the base angles theorem and the converse of the base angles theorem. Basically says if you have an isosceles triangle in the first one, as noted by the sides, the two sides being congruent, then the base angles B and C must also be congruent. And then the converse of that, if you have a triangle in which you have two angles congruent, consider those the base angles, then the two sides, in this case AB and AC, would be congruent, and this would be an isosceles triangle. So an isosceles triangle implies the base angles are congruent. If the base angles are congruent, it implies you have an isosceles triangle. Pause if you need to. Here we have a couple of corollaries. Basically, if you extend the idea of isosceles to equilateral, if a triangle is equilateral, then it's equiangular. So if the three sides are congruent, then the three angles are congruent. And the other corollary, if it's equiangular, then it's equilateral. So if you know the three angles are congruent, then that tells you the three sides are congruent. Again, pause if you need to. And finally, the hypotenuse leg congruence theorem for our theorems. What you need to understand about this one, it has to be a right triangle. So you see that the right angles here are marked. And you have to know that the hypotenuse are congruent for both triangles. The hypotenuse, remember, is the side opposite the right angle. So in this case, AC and DF are congruent. And that a corresponding set of legs are congruent. So either I have, as we do in this picture, BC is congruent to EF, or I would have had AB was congruent to DE. So I would have had to have both the hypotenuse and the leg of a right triangle being congruent to the hypotenuse and same corresponding leg of the other right triangle. If that's true, you can actually say these triangles are congruent. And this is the only one that breaks the angle side rule. And the reason that it gets away with it, so if you look at this, you would think, well, angle side, and we were told not to make an angle side out of ourselves. But here's what happens. Because these are right triangles, we can use the Pythagorean theorem to find the missing side. The missing side is going to be the same because there's only one side left in the Pythagorean theorem, a squared plus b squared equals c squared. If you plug in the same two numbers in both cases, the third number is going to be the same. So you're going to get the same length for AB and DE, which means in reality what this theorem leads us to is side. So it's not that angle side is actually working here, it's that because the angle was a right angle, this actually pushes us into side. We call this the hypotenuse leg theorem. You can abbreviate it with HL. Again, pause the slide if you need to. Also need you to recall a couple things about isosceles triangles. So where we have these congruent pieces here, then from our base angles theorem a little while ago, if these are the two congruent pieces, then the angles opposite this congruent side. So one is opposite this kind of upper right side, and angle 2 is opposite the lower side here. Those are considered the base angles. The angle that's in between the two congruent sides, so the two congruent sides make up that angle, that is the vertex angle. So you need to be aware of those things. And the side that is connected by the two base angles is known as the base of the isosceles triangle. Okay, this is going to be a very proof-intensive lesson. So we're going to go through several proofs. So for those of you that have been struggling with proofs, this is a good lesson for you. Give you a little bit more practice on what you can expect in the proofs. Because this chapter has a lot of proofs in it, you can expect that you're going to have to do a lot of proofs on the test. So in this first one, let's talk about what is actually going on here. So we have that YW bisects XZ. What that really means, YW, this vertical line, is splitting the base into two equal parts. So I'm going to mark XW and WZ as congruent. It got split into two equal parts. I'm also given that XY is congruent to YZ, so we want to mark those. XY is congruent to YZ. So I have two congruent sides there. Now, here is again where the simple property that's so easily to overlook has to be utilized. YW is a shared side for the triangle on the left and the triangle on the right. It would be congruent for the triangle on the left versus the triangle on the right. It's congruent to itself. So YW is congruent to itself. Given that, what I have is three sides of one triangle, the one on the left, congruent to three sides of another triangle. So the triangle on the left is congruent to the triangle on the right by side, side, side. What I'm trying to prove is not that the triangles are congruent, but that these particular angles, XYW, which is the angle up here, is congruent to ZYW, the angle here. My goal is to prove they're congruent. Well, if these two triangles are congruent, then their corresponding parts are congruent. So I'll actually be able to make this statement that those two angles are congruent to each other by CPCTC. Corresponding parts of congruent triangles are congruent. Now I'm going to show you a different kind of proof just so that you have some exposure to it, not because I think it's any better than a two-column proof. Recall that the real proof is a paragraph proof. That's where we want to get to in the end. We're going to still stick with two-column proofs, but what you're going to see here is a flowchart proof, just to give you a glimpse of what that looks like. So as you see, what we're going to do is say side, 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 and then use the fact that the two triangles are congruent to say that the corresponding parts, these two particular angles, are congruent. So here's how it'll look in a flowchart proof. So what you've got in a flowchart proof is anything that you can tell from the picture or from the given, independently of anything else. Gets its own kind of starting box. So the way that's going to look here is the given that YW bisected XZ got its own starting box. The given that XY was congruent to YZ got its own starting box. And because from the picture we were able to say, hey, YW is congruent to itself by the reflexive property, it gets its own starting box. So all of that given information at the beginning gets its own separate starting box. And then we let that kind of flow into whatever it is we're trying to prove. So the fact that YW bisected XZ, we'll start there. So I'm going to go down, and that implies that XW is congruent to WZ. XW is congruent to WZ, and that was the definition of a bisector. Okay? Now, knowing that this segment here, XY is congruent to YZ, and this segment here, YW is congruent to WY, or YW again, and this one, XW is congruent to WZ, those are the three corresponding segments for the two triangles that are all congruent. The YW was congruent to YW, remember, because of the reflexive property. We had this one from the definition of the bisector, and this one was given to us. So what we've just said, and I'm going to go back to the picture before so we don't get confused on this. We've just talked about the XW being congruent to YZ, the XY being congruent to YZ, XW being congruent to WZ, and YW being congruent to itself. That's what we've just stated with those three boxes that I had circled in the flowchart proof. And so that's going to allow us to make the statement that the triangle on the left, XYW, and the triangle on the right, ZYW, are congruent to each other. So here we are with those three statements that we were talking about. And they are all going to lead us to the statement that XYW is congruent to ZYW. So all of them have an arrow going to that statement. And that's going to be by the side congruence. Well, if those two triangles are congruent, then their corresponding parts are congruent. So in triangle XYW, angle XYW would be congruent to angle ZYW because they're in the same order of letters. So I can actually make the statement that those two angles we were asking about are in fact congruent by CPCTC. Okay. Again, it's a little different than what you're used to, but I want you to have a little bit of exposure to that type of proof. We're going to do another one with a flowchart proof. This one we start with PR bisecting angle QPS and angle QRS. Now let's talk about what that means. If PR bisects angle QPS, QPS is this big angle here on the left. So PR has bisected it, so it's split it into two equal parts. But it's also bisected angle QRS, the big angle on the right. So it splits it into two equal parts, not necessarily equal to the two for angle QPS. Okay. And we're trying to prove that PQ is congruent to PS. So we're trying to prove that the upper left and the lower left segments are congruent to each other. Well, what I already know is that PR is congruent to itself. Well, if I look now, I've got single arc, one tick mark, and a double arc on the triangle on the top, PQR, and the triangle on the bottom, single arc, single tick mark, double arc. So the triangle on top, PQR, and the triangle on the bottom, PSR, are going to be congruent by angle, side, angle. So we'll use that then to say then the corresponding parts of PQ and PS have to be congruent by CPCTC. But we have to start by showing the top and bottom triangles are congruent. Okay, so here is the flowchart proof. The two things that are independent are given, which was that PR bisected those two angles, but also our reflexive property. We just pulled that from the picture. We didn't have to have anything else to tell us that other than the picture that was given to us. So those two things are separate entities that we can start with. Now, the fact that PR bisected those two angles leads us to these statements. That angle QPS was bisected into QRP and SRP, and angle QRS was bisected into angle QPR and angle SPR, both sets of angles being congruent. Okay? So now I have two sets of congruent angles. So I'm going to lead from there to this statement, but I have to couple it with my RP being congruent to itself by the reflexive property. When I put all those pieces together, I can actually state that the two triangles are congruent by angle, side, angle, as we said when we looked at the picture. And if that's true, then I can say that the corresponding pieces of PQ and PS are congruent. So those segments are congruent, and that's by CPCTC. Corresponding parts of congruent triangles are congruent. Okay, here we're given that these two segments, NO and MP, are parallel. So what I'm going to do is mark that they're parallel to each other. NO and MP. And that angle N is congruent to angle M. Or I'm sorry, angle P. Angle N is congruent to angle P. So these two are parallel, and these two angles are congruent. Well, if these two are parallel, then, and I've got this line OM running through here, it's acting like a transversal. So I'll be able to say that this angle up here, NOM, and this angle down here, PMO, can be congruent to each other by the alternate interior angles theorem. So I've got now two sets of angles in both triangles, the upper triangle and the lower triangle, that are congruent. But they also have a shared side, MO. So MO is congruent to itself. Well, that means I've got a single arc, a double arc, and a single tick in the upper triangle, and I've got a single arc, a double arc, and a single tick in the lower triangle. So I've got angle, angle, side, saying that these two triangles have to be congruent. Triangle NOM has to be congruent to triangle NMO by angle side. Well, if that's true, then I can make the case for these two sides MN and OP being parallel in a couple of different ways. I could use a third angles theorem to show it. For one, I could use an alternate interior angles theorem by saying that the triangles had to be congruent, so therefore their corresponding parts are congruent. So I have some different options for how I go from there, but in the end I'm going to be able to show that MN and OP happen to be parallel. So let's see how it would look in a proof. So we're beginning with our given that N and P, those angles were congruent, and that NO and MP were parallel as we marked in the picture. So recall that we did that, and then after that we talked about the fact that NO and MP being parallel meant that we had alternate interior angles that were congruent. So angle NOM is congruent to angle PMO by the alternate interior angles theorem. And then we pulled our reflexive property that MO was congruent to itself. So nothing that should shock you here, as we just went through it in the picture. So we've got those pieces of information laid out for us, which are actually between angle N being congruent to angle M, or I'm sorry, angle P, and angle NOM being congruent to angle PMO, and MO being congruent to MO as segments. That's enough to say the triangles are congruent by angle side. So these two triangles are congruent by angle side, and now we want to be able to show the parallelness of the side on the left and the side on the right. So what we're going to do is state that angle NMO is congruent to angle POM as a result of CPCTC. Realize we didn't actually have to go through the congruence here, because once we had the two angles in the two triangles that were congruent, we could have been able to say that this angle was congruent to this one by the third angles theorem. So just a couple different ways you could have done this proof. So you could have bypassed angle side and CPCTC and actually went straight to this step if you remembered the third angles theorem. Okay. So what we're going to do, I'm going to go back to the slide with the picture on it just so that we can see what this looks like. What we've now been able to say is that this angle and this angle are congruent. Well, as we have an acting transversal here, these are alternate interior angles for sides MN and OP, which means I'll be able to say by the converse of the alternate interior angles theorem, or the alternate interior angles converse, that those two lines are parallel. So MN is parallel to OP by the converse of the alternate interior angles theorem, also known as the alternate interior angles theorem converse. Okay, here I'm given that J is the midpoint of K, M, and NL. So I would mark what that means for me. J is the midpoint of KM, then KJ is congruent to JM. And J is the midpoint of NL, then NJ and JL have to be congruent to each other. So now I have two sets of congruent sides based on whichever triangle I want to choose. I'm wanting to prove in the end that KL, this top line, and MN, the bottom line, are parallel. So what I'll probably want to do is use the triangle here and the triangle here as the basis for my proof. Well, what I know is vertical angles are congruent, so angle KJL is congruent to angle NJM. Well, I've got side, included angle, and another side. Side, included angle, and another side. These two triangles are congruent by side, angle, side. And if they're congruent by side, angle, side, then I'll be able to show through the use of CPCTC, corresponding parts of congruent triangles are congruent, that, for example, this angle, KLJ, and this angle, J and M, happen to be congruent. And if they're congruent, they're alternate interior angles for KL and NM, so KL and NM have to be parallel. So that's where we're going with this. So we'll use the converse of the alternate interior angles theorem again. in the end to show that the lines are parallel. Recall that you always have to have a converse rule to show parallel. Okay, so now that we understand where we're going with the proof, let's actually talk about the proof itself. So we begin with our given, that J is the midpoint of Km and NL, and then what that means for us. That Kj is congruent to Mj and Nj is congruent to Lj. And that was just the definition of a midpoint. So it split the two line segments into equal parts. Then we talk about vertical angles. Again, the ones going up and down in the picture, that angle KJL and angle MJN had to be vertical, and vertical angles are congruent. So now I have enough to say that the triangles are congruent by side angle side, which is what we're doing here. Triangle KJL congruent to triangle MJN by side angle side. And as I said, that's going to let me state that there's two angles, one in each triangle, that are congruent by CPCTC. And in this case, LKJ and MNJ. And those represent alternate interior angles for the top and bottom line of the picture. And since the alternate interior angles are congruent, the lines have to be parallel by the converse of the alternate interior angles theorem, which is what we wanted to show, that the two lines were parallel. Okay? So if you need to, go back and look at the picture again. You can come back and look at the proof, pause between two. You can take a screenshot if that helps you to have the picture in front of you looking at the proof. But fairly straightforward proof. These are the types of proofs you can expect to see on a quiz or a test. Okay, here you're going to have to be able to pull some pictures out of this one in your mind. So we'll kind of draw some off to the side as we need to. You're given an isosceles triangle, PQR, with base QR. Now let's talk about what that specifically means. Base QR. That means this is the part that's not necessarily the congruent side for the triangle. So what is a congruent side is PQ and PR. Those two full sides are congruent to each other because this is an isosceles triangle. It's the definition of an isosceles triangle. We also know that PA and PB, these smaller sections, happen to be congruent to each other. We'd like to prove that that means that AR and BQ are congruent. So AR is the diagonal line going down from left to right, and the diagonal line BQ, the one going down from right to left. We'd like to show those are congruent. Here's how we can do that fairly easily. We have to be able to see a couple of triangles in this picture that are inside the picture. Specifically, and I'm going to change the color up here, I need to see this triangle. So PQB, if you want to call it that. And then I need to see another triangle that's kind of overlapping with that one. PAR. Those are the two triangles I'm going to be looking at. Now, what I know about those two triangles, and it's hard to see right now, and I'm going to redraw them for you, but what I already know about those two triangles is two congruent sides. You see, in the red triangle, I know PA, and I know PR. That's what this long purple line over here, remember, it's congruent to PQ. So I know this whole side here and the side over here. That's two sides. Well, the same thing in the green triangle. I know this short side, PB, but also know the big side, PQ. Well, they both share an angle. If you look closely, they both have this angle P in them. So I can say that angle P is congruent to itself by the reflexive property. That's going to give me two sides and an angle. Specifically, two sides and an included angle. I'm going to be able to say those two triangles are congruent by side angle side, which will allow me to use CPCTC to state that AR and BQ are congruent. So let's draw these triangles again real quick. The red triangle, and this isn't going to be real pretty, but it'll be enough to give us the idea. And then the green triangles, let me change colors here. The green triangle, okay, so it's going to look something like that. And this top piece here for both of them is P. I've got B over here and Q down here for the triangle on the right. And let's change colors here. And I'll rewrite P here in red just so we're not confused. And I've got R here and A here. And what I know is that PA is congruent to PB, and I know that PQ, or PR, the long side here, is congruent to PQ, this side here. So by stating that angle P has to be congruent to itself, I have side, angle, side, side, angle, side. So these two triangles will have to be congruent, and therefore their corresponding sides of AR and BQ would have to be congruent by CPCTC. That's how we're going to do the proof. Pause the slide if you need to look at those pictures a little longer to take that in. So here's the proof. We start with isosceles triangle PQR and base QR. That was given to us. So we talk about which sides are congruent from the isosceles triangle, PQ and PR. That's by the definition of an isosceles triangle. Simple enough there. Now, PA and PB were also given to us as congruent. So now we've used all of our given and the definition of the isosceles triangle. So we've got two sets of sides that are congruent. Those two sets of sides are going to be involved in those two triangles that we drew out to the side. Now recall that angle P had to be congruent to itself by the reflexive property. You're going to always say something is congruent to itself. That's a reflexive property. So I now have the two sets of sides and the included angle P. That's going to let me make the statement about the two triangles being congruent by side angle side. So triangle QPB is congruent to triangle RPA by side angle side, which then lets me make the statement that the two corresponding sides are congruent by CPCTC. So AR is congruent to BQ by CPCTC. Okay, here I'm going to use the fact that X is the midpoint of AC and angle 1 is congruent to angle 2. If X is the midpoint of AC, what I can actually state is that AX is congruent to XC. So, a little shout out to our cross-country folks. But AX and XC are congruent, and angle 1 is congruent to angle 2. Angle 1 congruent to angle 2. So I've got a set of sides and a set of angles that are congruent for both. Well, this one's pretty simple as to how I'm going to show that X is the midpoint of BD. That's what I'm trying to prove here. I'm just going to show that the triangle on the left, so AXD, is congruent to the triangle on the right, with BX and C as sides. And how I'm going to do that? Vertical angles. This angle here is congruent to this angle here by vertical angles. So AXD is congruent to BXC by the vertical angles theorem. That's enough to give me angle, side, angle. Angle, side, angle for the two triangles to be congruent. And if they're congruent, then their corresponding pieces, XD and XB, have to be congruent, which would imply that X is the midpoint of BD. So take a little longer look at the picture if you need to by pausing the video. So X was the midpoint of AC and 1 was congruent to 2. That was our given. We then used the definition of the midpoint to tell us which segments of that, pieces of that segment AC had to be congruent, AX and CX, by the definition of congruent segments. Or actually, it's by the definition of midpoint, so we should correct that. Let me do that real quick. So change that to midpoint. Okay, so definition of midpoint is where that actually came from. And then the two angles being congruent by the vertical angles theorem, the ones that were going left to right there in the center. We already have this set of angles that are congruent. Here's the included side. Here's another set of angles. So the triangles were congruent by angle, side, angle. With them being congruent, we could use CPCTC to tell us that our corresponding pieces of DX and BX are congruent. If they're congruent, then they're equal in length by the definition of congruent segments. And that tells us that X had to be the midpoint of BD because it split BD into two equal parts. Okay. All right. Here, I want to find the measure of angle F, knowing that this is an isosceles triangle. So what I have is a vertex angle that's 22 degrees. I know that the triangle sum theorem tells me that all three angles in the triangle have to add up to 180 degrees. So I'm going to remove the 22 degrees from 180. That's going to leave me 158 degrees. But the base angles theorem tells me that if the two sides of this triangle are congruent, then the base angles, D and F, have to be congruent to each other. So angle D and angle F will have to be congruent. So I'm just going to take that 158 and split it between the two, which is going to give me 79 for each of them. So I start with the fact that I know the measure of angle F had to be equal to the measure of angle D, which we're just going to call X. So I'm just going to plug in X for both F and D to set this up algebraically. And then I will, again, sorry, another typo here, so let me make a quick correction. This should be E. So the measure of angle F plus the measure of angle D plus the measure of angle E would equal 180 degrees, whereas E is 22 degrees as part of that equation. Okay, so X plus 22. This is just the algebraic way of setting it up. If your mind thought the way we talked through it before, just do it the way we did. You don't have to write it out algebraically to solve this. But you're going to get 79 degrees either way. Okay. Take a little longer to look at that if you need to by pausing the video. Otherwise, we'll move on. So here I want to find the measure of angle G. Well, I noticed that by the two sides that are marked as congruent, that angle G and angle J have to be congruent to each other. Well, I've got algebraic expressions for both, so set them equal to each other. So x plus 44 equals 3x. I'll subtract x from 3x. It's going to give me 2x equals 44, dividing by 2, and I'm going to get x is 22 degrees. It's asking me in this problem to find the measure of angle G. G is represented by x plus 44, so I'll just take that 22 and I'll plug it in for x. 22 plus 44 is 66 degrees. So the measure of angle G is 66 degrees, which means the measure of angle J is 66 degrees. So if I asked you to go on and find me all the angles, J is going to be 66, G is going to be 66. That's a total of 132. That's going to leave you 48 degrees for H, because all three have to add up to 180 degrees. Here I have an equilateral triangle and they gave me one angle. Now I don't have to set all three of these equal to 2x plus 32 and add up to 180 degrees. Because recall, if a triangle is equilateral, it's equiangular. If it's equiangular, all three angles are 60 degrees. So I can just simply set the 2x plus 32 equal to 60 degrees. That's the easiest way to approach this problem. Is it wrong to plug in 2x plus 32 into each of the three angles? Absolutely not. You could do that, add that up to 180. You're still going to get the same answer. It's just quicker to go this way. So 2x plus 32 equals 60. So I'm going to subtract 32 from 60, leaving me 28 degrees. So 2x equals 28. And then I'm going to divide 2 into the 28. And I'm going to get that x is 14. Since that's all I had to find here, the value of x, we're done with this one. Again, pause if you need to. Here I want to find the value of y. I see that the triangle is equiangular. If it's equiangular, by one of our corollaries, it's equilateral. So that tells me that I can set these two pieces, 5y minus 6 equal to 4y plus 12. I'm just going to set them equal to each other and solve for y. So when I do that, I will subtract 4y from 5y, and I will add 6 to 12. I'm going to get that y is equal to 18. That's all it was asking me to find, was the value of y, so we're done with that. Here I want to determine if I can use the HL congruence theorem to prove the triangles are congruent. Remember in the HL, the hypotenuse leg, you need to know that the hypotenuse of two right triangles are congruent and that a leg that is corresponding for both of them are congruent. Well, first thing I got to know is, do I have two right triangles? Well, linear pair postulate says that linear pairs are supplementary. And one of our theorems told us that if we had congruent, we have a right angle here. So if we have a right angle, linear pair has to add up to 180. If one of the angles is 90, the other angle is also 90. So I can mark this as 90 degrees. So I'm going to do that right there. Now I've got two right triangles, and I've got a set of hypotenuse for each of them that are congruent. Now if I only had enough information to tell me that they had another side that was congruent, I'd be done and I could use hypotenuse leg. Well, I do. They share a side. So this vertical side is congruent to itself by the reflexive property. That's enough to tell me that I have two right triangles in which the hypotenuse and a corresponding leg are congruent. I can use the hypotenuse leg congruence theorem to say that the two triangles are congruent. Okay. So this is just a summary of what I just said. If you need to read through that, look at the triangle a little longer, feel free. Otherwise, we'll move on. Here we want to know if we can use the hypotenuse leg congruence to prove that the triangle on the left is congruent with the triangle on the right. We've already got that they're two right triangles because we see the right angle in each. And we see the side opposite the right angle is congruent, and those are the hypotenuse. So once again, if I had a shared side or a corresponding set of sides that's other than the hypotenuse that are congruent, I can use hypotenuse leg. Well, I do, because CB is congruent to itself by the reflexive property. Since it's congruent to itself, that's enough to give me the hypotenuse of a right triangle and a leg for each right triangle. And that's enough to tell me the two triangles are congruent by the hypotenuse leg theorem. So I would actually be able to say triangle ABC is congruent to triangle DCB by the hypotenuse leg theorem.